I'm going to skip over some of the motivations because Lars typically talks about this big data analysis, that he does a very good job of it, and I don't want to basically spoil it for you. But basically the idea here is that there's a lot of data available nowadays. Specifically if you look at terrain data, and this data comes from satellites where they measure heights of different points. So for example, if you measure the whole Denmark with the resolution of 1 point or like half meter, you get this many amounts of data, which is very big. And in fact, when it comes to applications such as predicting floods and stuff like that, having high resolution data, it makes a big difference. It gives you much more precise predictions compared to, let's say, the left prediction is wrong, the right hand prediction is correct, and you only get this because your data is more accurate. But of course, if you have very high resolution data, your data size is also big. So therefore you will need algorithms that can scale with the data size. And this, brings up many technological challenges as well as industrial challenges and etc. Again, Lars does this much better than I can do. But so I'm just going to skip that part and just go towards the algorithms. The first thing we're going to look at are queues and stacks. This is very interesting because these are relatively simple data structures. So what is a queue? So queue is a data structure that has two operations, a push operation and a pop operation. When you push it at the beginning of the queue, and when you pop, you push it at the end of the queue. When you pop at the beginning of the queue. These two operations can be easily implemented in the IO model by just having two elements, two blocks, one for push and one for pop. We're going to look at the more details of them in the exercise classes. So let's move forward. You can do the same thing with a stack. So stack is more or less the same thing, except that you push and pop from the same location, so from the same end. And the next example is merging. And now the idea here is that we could sort M over B sorted lists, we can merge M over B sorted lists in essentially O of N over B IOs. Again, I'm going to skip the details of this. We're going to look at the details in the exercise classes. And similarly, the other problem is that we can distribute an unsorted list into M over B list using M over B splitting elements. So for example, we can think of it as the generalization of a quicksort. In the quicksort algorithm, you have one element and you want to split the array into two halves, one half that is smaller than the pivot and the other half is larger than the pivot. Here we have essentially M over B pivots, and we want to split this list into that many sublists. So with those things, we can actually solve the sorting problem. So how does sorting look like? Well, we could do merge sort. We could start by creating, let's see if I can add it. We create N over M sorted lists. So inside this list there are M elements. So the number of these elements is N over M. And we can sort them initially. Just read all of these elements. They all fit inside memory because they're M elements. We sort them inside the internal memory and then write them to the disk. Then we load all of these M elements to the memory, sort them and write them to the disk, etc. Each one of these requires N over B IOs. The number of lists is N over M. So the total number of IOs is going to be this. And as you can see, this is essentially exactly equal to N over B. So with N over B block reads and N over B block writes, I could sort all of these initial lists. Let's see. After doing that, then we can do the merging operations repeatedly. So if you go back here I claim that if I have less than m over b sorted lists, then I could merge them in total of n over b IOs. Okay, so that's what I do here. I have n over m lists, group them into groups of size m over b lists. So here I have m over b lists. I merge all of them into one bigger list. Similarly, I do the same thing with the next m over b lists, and so on. Merging all of these lists take essentially scan time, because I just read and write every block constant number of times. So this merging step in total will take O of n over b IO. The number of lists will go down by the factor m over b, which for simplicity we use a small m to denote it. So therefore over here I have n divided by m divided by m lists at this point. Again, then I grab m over b of them, or a small m of them, and I merge them into one list. So over here I will have nm divided by 1m 1 over m squared lists at this level, and so on. If you continue this operation, the number of lists goes down by a factor m at each operation. So the total number of levels is going to be log base m of n over m. After this many levels, I will have only one list left, which obviously will be sorted. At each level I use n over b IOs, so therefore the total amount of IOs that I use will be n over b times that log factor. So basically this is what I have here. So that's what it takes to sort using merge sort.